Hello, this is Shushmita. Today we are in session 4 of Units and Measurement, and we are going to talk about errors today. We are going to solve a lot of problems. I will later on I will take a video session to solve all the homeworks. I have given you a homework in this session also. Look in the description box below. So let us get to our session. Whenever we are making a measurement, we are also making an error. And it is important to understand the amount of error that is present in our measurement, and it is also important to understand the extent up to which we can afford the error in our measurement. If we are measuring the distance between Earth and Sun, then an error which is of the order of a few kilometers does not matter. Even if it is 10 kilometers, it does not matter while we are measuring the distance between Earth and Sun, because this distance is of the order of 147.43 into 10 to the power 6 kilometer. So in this huge amount, 10 kilometer is insignificant. But we cannot afford to make even an error of 1 kilometer while we are measuring height of a person, because ideally height of a person varies between say 160 to 180 centimeters, which is much less than 1 kilometer. We cannot afford to make an error which is of the order of even meter or even of the order of a few centimeters while measuring the height of a person. So it is important to know that our system has error. It is also important to find out how much error is present in our measurement, and thereafter to nullify that error and to believe in the accuracy of our data. It is also important to know if we can afford that amount of error in our measurement. Errors may occur during measurement due to different kind of reasons, and they are broadly classified into two types. One is the systematic error that can be nullified by taking multiple measurements on the system, and another one is the random error that is always present in the system and cannot be totally nullified. One easy example of systematic error is measuring length of an object with a metal ruler. Metals expand due to metals show a phenomena that is called thermal expansion. That means if provided with heat, metal increases in length as well as breadth, and if they are again cooled down, they contract in length and size. Therefore, if we make a scale using a metal, it will expand during summer and it will contract during winter. Therefore, the interval between two lines on the scale will also vary. It will not ideally be 1 centimeter. It will keep on varying on summer and winter. So if we measure the height of the same person in summer and winter, it will give me different values. Offset error, on the other hand, is that kind of error when our system's zero is not calibrated. We will talk about this when we learn about vernier calipers and screw gauge. Another kind of offset error that we see in our everyday life is when we go to the grocery store to buy something that they sell in terms of kgs, and we always see that even if we want to buy something of 40 kg, but we are getting that in 39 kgs, because this system has an offset error of 1 kg within it. So whenever you try to measure something that weighs say 50 kg, that balance will show 49 kg instead. So there is always an offset of 1 kg. If we are aware of that, we can add that 1 kg to our measurement given by the instrument, and we can get our true value. So if we have the perfect knowledge, it is possible to nullify the systematic error from our measurement. Now, did you know that height of a person increases when he is lying down rather than when he is standing up? This is also one kind of systematic error. So if you take the measurement of height of a person who is standing, the value that you will get a little slightly larger value when if you take the height of a person when he is lying down on a table. And this happens due to the presence of gravity on earth. Random errors, on the other hand, may occur due to the judgment of the observer. It also depends on the memory of the observer, the perception of the observer. Suppose this is a volume measuring beaker. You can see this in your home in the cup syrup or with any kind of syrup. They give a volume measuring cap, and there you can see there are lines like this drawn on the cap that tells you the value in terms of, say, milliliter. So this is 0.1 milliliter, 0.2 milliliter, or in our case let us say 1 milliliter and 2 milliliter, 3 milliliter and so on. So suppose you are measuring the length of the liquid and the volume becomes 3 ml, and this is 3, but each and every time we try to look at it, our eye may not be in the normal position every time. So each and every time our measured value will differ slightly from the previous value, and this is one kind of random error that is present in the system. If we take two observers, say person 1 and person 2, we ask them to measure the volume of the liquid on the beaker, they will give you a value that will differ for sure because of this kind of error, and it cannot be totally nullified. The same error occurs when you try to weight yourself on a scale. So you stand on the scale, each and every time you look down to see your weight that the measuring equipment is showing, that value will keep on toggling. So that is also another kind of random error, and these errors are always present in the system. We can try to minimize them by taking the measurement multiple number of times, finding out the standard deviation or the standard error, and then deducting that standard error from our measurement. So while we are taking a measurement, we will also learn how to find out the standard error present in the measurement. Look at this quantity. These are some data of observation provided. The method is to first find out the sum, which is 30 plus 30, 60 plus 100, 60 plus 40, which is 140 plus 50. So this is 100 plus 50, it becomes 150. This is the sum, and if we take the average of the quantities, let us take these are the values for a variable x. So the average is 150 divided by the number of measurements taken, that is 1, 2, 3, 4, 5. So 150 by 5, that is 30. This is the average. Now we define a quantity as the standard deviation, and the standard deviation is nothing but root over the value minus the mean whole square divided by again the number of measurement, that is 5, and we want to take this from I equal to 1 to 5 because we have total 5 measurements. So let us calculate this quantity for each of the data provided over here. Let us take x equal to 10, and for that our x minus x mean becomes 10 minus 30, which is minus 20. For x equal to 20, our data becomes 20 minus 30, which is minus 10. For x equal to 30, it becomes 0. For x equal to 40, it again becomes 40 minus 30, which is 10. And for x equal to 50, it becomes 50 minus 30, which is equal to 20. Now we put all the values. So this becomes root over minus 20 square, that means 400, plus minus 10 square, which is 100. Next one is 0, and the next to next one is again 100 plus again 400. So this becomes 100 is 200, this is 800, so 800 plus 200 is 1000 by 5, which comes out to be 200, root over 200, that means 10 root 2, and root 2 is nothing but 1.414, so this becomes 10 into 1.414, and now this becomes multiplied by 10, so 14.14. So the standard deviation in the measurement of our data is of the order of 14.14. Thus we should know that if in this scale we are taking a measurement as 10, then this 10 might fall in the range this. So there is an error of the order of this in our measurement. Moving on further, suppose we are given two quantities in the form a minus b, a plus b, or a minus b. So they are connected by addition or subtraction, and the error in the measurement of a is provided as delta a, and the error in the measurement of b is provided as delta b. Then the error in the measurement of z will always be delta z. The error present in the measurement of z will be added up. And here, though these two quantities are subtracting these two quantities, but error is always additive. So the error will also add up in this case as well. So suppose one of the length measurement in a scale is given to be 5 centimeter plus minus 0.01 centimeter, and another length is provided to be 6 centimeters plus minus 0.02 centimeters. So if we add these two values, if we want to add, these two will add up and our errors will also add up. So in the final measurement, error will increase, and it is the same for this one. Though the quantities are connected with a subtraction sign, that does not mean that errors will be subtracted. Errors will be added in the measurement. In case of error of a product, it is a little bit different. So if we are to calculate the product, the error in the product z, we can write it as the error in measuring z is written as delta z over z is the sum of the products, sum of the errors in measuring a and b, and it is written as this. Same in the case of a division. Look into this quantity that is raised to some power. So z is equal to a to the power p, b to the power q by c to the power r, and it is given the error in measurement of a is delta a, that in b is delta b, and that in c is delta c. We want to find out the error in the measurement of z. So we can write the error in the measurement of z as the error in the measurement of a multiplied by p plus the error in the measurement of b multiplied by this power q, and the error in the measurement of c as r delta c by c. So this is our error. Now this is the relative error, and it can also be written in the percentile form if we multiply this by 100. So if in the problem you are asked to find out the percentage error, the thing that we have to do is only multiply this each quantity by 100. So that was what I was talking about. This is the percentage error. Suppose we are measuring weight using a balance, and the true value should come as 40 kg. We are measuring a weight of 40 kg, but each and every time we measure the quantity, we have taken 5 measurements, and due to some or the other error, The measurement has come as 40.1 kg, 40.05 kg, 40.2 kgs, 40.06 kgs and 40.3 kgs. So the relative error that we just now had written as delta A by A is defined by this. That means the measured value, let us take this data, and 40 is the true value divided by the true value. This is called the relative error. So this is the delta part and this is the true value. And in case of a percentage error, what we do is we write the same thing and we multiply it by 100. This formula is wrong over here. We have to multiply it by 100. So that is our percentage error. This is the first problem. It was asked in NEET 2013. In an experiment, 4 quantities A, B, C, D are measured with relative percentage error of 1%, 2%, 3% and 4% respectively. Therefore, we know that delta A by A is 1 into 100%. Similarly, for the quantities B, C and D. Now, they want us to calculate the error in the quantity P, which is A cube B square by C into D. They want us to calculate the percentage error. Now, the relative error is 3 into delta A by A plus 2 into delta B by B plus delta C by C plus delta D by D. Now we are given the values of these quantities. 3 into 1. Now this is the percentage error, so we will have to multiply it by 100. Or what we can do is we can keep the 100 for the last. Plus 2 into delta B by B is 2 plus delta C by C is 3 and this is 4. So this becomes 3 plus 4 7 plus 3 10 plus 4 14. So delta P by P, even if we multiply this by 100, we will also have to multiply this side by 100. So let us ignore the 100 because they will cancel out and the percentage error in this will come out as 14%. Hope this is clear to you. Let us now take a little complicated example. Suppose a quantity is given. A is equal to root over P Q divided by R square into S cube. And the error in measurement of P is 1%. That in measurement of Q is 3%. R is 0.5% and S is 0.33%. We want to calculate the percentage error in the measurement of A. So the percentage error will come out to be P to the power half, means half into the percentage error in P. Q is also under root over, so that means Q to the power half, and this is the percentage error. R has a power of square, so 2 into, and S has a power 3. So half into the percentage error in P is given as 1. Half into percentage error in Q is given as 3. 2 into percentage error in R is given as 0.5. And that in S is given as 0.33. So it becomes perfect example of 0.5. 3 by 2 is 1.5. This is 1 and this is 0.99. So our answer becomes, this is 2, this is 3, 3.99. This is the percentage error in the measurement of A. This is another type of question that may be asked in the examination. Here they have given that A student measures the distance traversed in free fall of a body. It was initially at rest. He uses the data to estimate g, the acceleration due to gravity. If the maximum percentage error in the measurement of the distance is E1 and that in the measurement of time is E2, then what will be the percentage error in the measurement of g? So we know that in case of a free falling body which is falling from a position of rest, let us consider this distance as d and time taken to fall is t. We can use this equation. So our distance is d, initial velocity is 0, acceleration is acceleration due to gravity, and this is time. So the student uses this value to calculate that of g. So g becomes 2d by t square. So the error in measurement of g becomes the error in d plus, as it has a power of square, so 2 multiplied by the error in measurement of time. And our percentage error in measurement of d is given as E1 and that in measurement of t is given as E2. So this is the maximum percentage error that can happen in measuring the value of g if we use this equation. This is another type of example. If the error in the measurement of radius of a sphere is 2%, this is the percentage error, what will be the error in determination of the volume of the sphere? We know that we can write the volume of the sphere is 4/3 pi r cube. Therefore, the error in measuring the volume is 3. This 3 into percentage error in measurement of r. So 3 into 2, that is 6%. The problems are very easy. You only have to understand the basic of it. Ignore the constants in error measurement because they will remain the same. They do not have any error in them. This is our next problem. So they want to find the acceleration due to gravity using a simple pendulum. We know the equation. The time period for a simple pendulum t is 2 pi root over L by g. We can reduce this equation using the dimensional analysis, just like we did the time in case of free fall, which is h over g into some constant. So from here, if we take square of both the sides, we get, and that gives us g is equal to 4 pi square L by t square. So the error in g is the error in L plus 2 into the error in t. Now these two quantities are given but indirectly. Look into this. The time period of 0.5 second is measured from time of 100 oscillations with a watch of 1 second resolution. So this is our delta t, 1 second, and t is 100 into 0.5. So our delta t by t is 1 over 100 into 0.5. Next, let us look for delta L. If measured value of length is 10 centimeter known to 1 millimeter accuracy, that means our delta L is 1 millimeter, which is 1/10 of a centimeter, and our L is 10 centimeter. So our delta L by L is this 1 over 10 and L is equal to 10. So 100, 1 by 100. So now delta t by t into 2 plus delta L by L becomes 1 over 100 into 0.5 multiplied by 2 plus 1 over 100. Let us take this 1 over 100 as common, so we are left with 2 by 0.5 plus 1. This quantity is 4. So 1 over 100, 4 plus 1 is 5. So this becomes 5 over 100. So if we are to get the percentage error, that means we have to multiply this with 100 and this becomes 5%. So our answer is 5%. This is our next problem. A student measures the time period of 100 oscillations of a simple pendulum 4 times and the data set is 90 seconds, 91 second, 95 second and 92 seconds. The minimum deviation in the measuring clock is 1 second, then the reported mean time should be. So there is some error in our calculations and the error cannot be this because this measures up to 0.1 second. This is also measuring up to 0.1 second because of the point 0. So this is also not our answer. This is not our answer. We are left with these two options. So I have told you in the standard deviation calculation, this first we should be calculating the mean of the data provided. So 90 plus 91 plus 95 plus 92. There are total 4 data sets. So we'll divide this by 4. That means 360 plus 718. 368 divided by 4 and it becomes 92. Our mean is 92. We could use the rigorous method of standard deviation, which is x minus x average squared by n, and I will show you what this gives you. For this data over 90 here, 92 minus 90 is 2, so we get 4 plus 92 minus 91 is 1, 1 squared is 1, 95 minus 92 is 3 and that square is 9, 92 minus 92 is 0 divided by 4, so this becomes 14 over 4 and this gives 1.8 which approximates to 2. We can also calculate it in a shorter way. We can find out the standard deviations. We can find out the errors in x. The true error that we measured I showed you, which is called the relative error. That means the measured value minus the true value. We will take the mean as the true value. So for our first data set, that is 90, it becomes 2. For 91 it's 1. For 95 it is 3. So our relative error is 6. If we are to take the mean error, it becomes 6 over 4 measurements. So this is 3 over 2 or 1.5, and if we approximate this, it again becomes 2 because the last digit is 5 and the digit before that is odd. So we will add 1 to it and it becomes 2. So this option is correct. This is our answer. Look into this problem. They have given us a quantity like this. They want us to find the error. So let us first forget about the errors and calculate the value of rho. W1 is given as 12. W2 is given as 10. So 12 minus 10, which is 12 by 2 and 6. Next, let us calculate for the error. So it is in the form of A by B. We know that if a quantity is in the form of A by B, then the error in the result is delta A by A plus delta B by B. So this will become delta W1 over W1 and our B is W1 minus W2. So plus delta W1 minus W2 divided by W1 minus W2. The error in the measurement of W1 is 0.04. W1 is given as 12 plus. We also know that if a quantity is given connected to each other through an addition or subtraction sign, then the error in the measurement becomes delta A plus delta B. So here W1 minus W2 are connected through a subtraction sign. Therefore, the error in the measurement of them will become the error in the measurement of W1 plus the error in the measurement of W2. W1 minus W2 is again 12 minus 10, which is 2. So this over here becomes 0.04 by 12 plus 0.07 by 2. This is our error. Let us calculate for this. Zero point 0.04 by 12 plus 0.07 by 2, which is 0.383. So this is 0.383, and if we multiply this by 100, it becomes 3.83%. So our row will have a percentage error 6 plus minus 3.83%, and we will write 2 zeros after this because we are measuring up to 2 decimal points. So let us go through the options given here. None of them is correct, but this one is close. So this is our correct answer. That is all about errors for today. Moving on, we'll solve lot more problems on errors, and our next session is going to be on vernier scale and screw gauge. So see you in the next session. Till then, take care.